Nuclear magnetic resonance, or NMR, is probably the most important technique for finding the structures of organic compounds. So much so that there is a saying, when the NMR goes down, the organic chemists go home. The principle of NMR is based on the fact that certain nuclei with odd atomic mass or atomic number, such as hydrogen 1, carbon 13, fluorine 19 and phosphorus 31, have a property called spin. This means that they have a magnetic field similar to that of a bar magnet. When placed in an external magnetic field, these nuclear magnets can line up in one of two ways, with or against the applied field. These two different states have slightly different energy levels. Electromagnetic radiation, which has an energy corresponding to the gap between these two states, can cause these nuclear magnets to flip from a low energy state to a high energy one. The size of the energy gap determines the frequency of radiation required. Each element has its own particular frequency, but they all lie within the radio part of the spectrum. We will concentrate on hydrogen 1 NMR. This is often called proton NMR because the hydrogen nucleus is just a single proton. As they drop back from higher to lower energy states, the nuclei of hydrogen atoms in different positions in the molecule give out energy at slightly different frequencies, and this can tell us a lot about the structure of the molecule. For example, in ethanol, CH3CH2OH, the three CH3 hydrogens will give a slightly different frequency than the two CH2 hydrogens, which will be different again from that of the single OH hydrogen. This energy is picked up by a receiver in the instrument and looks like this. A strong signal gradually dying away. This is the total signal from all of the hydrogen nuclei in the sample and is very difficult to interpret. However, a mathematical technique called a Fourier transformation can be used to separate out the signals from hydrogen atoms that are in different molecular environments and present them as a spectrum that can be interpreted by chemists. This is a typical NMR instrument. The magnet is a superconducting one and is housed inside the cylindrical metal casing. It is cooled to 4 Kelvin in a jacket of liquid helium, which in turn sits in a jacket of liquid nitrogen at 77 Kelvin. The magnet uses a current of 50 amperes, which, once started, flows continuously as the coils have zero resistance at 4 Kelvin. The sample sits in the centre of the cylinder inside this probe, which contains the coils that send and receive the radio frequency signals. The electronics which generate and interpret the radio signals are housed in the boxes to the left. Samples are placed in the machine and removed from it by the auto changer, which takes the samples in turn from the carousel. The instrument is controlled from this workstation. This spare probe shows the radio coils and where the sample sits. Here we will run the proton spectrum of ethanol. A small amount is taken and dissolved in deuterated trichloromethane. This solvent is trichloromethane, in which all the hydrogen atoms have been replaced by deuterium. This is so that the signals from hydrogen atoms in the solvent will not be mixed up with those in the sample. A little tetramethylsilane, TMS, is often added as a reference. Each molecule of this has 12 hydrogen atoms all in exactly the same environment. The signal from these is taken to be the zero of the spectrum and has the value of 0 parts per million. Inside the instrument, the sample sits on a cushion of gaseous nitrogen. This plastic spinner has vanes that turn in the flow of nitrogen and spin the sample. The spinner is placed on the tube in such a position that the sample tube will be in the centre of the magnetic field when it is in the instrument. Together, these ensure that the sample experiences a uniform magnetic field. The operator places the sample in the auto-changer and tells the computer the identity of the sample and which position in the carousel it is in. The auto-changer selects the correct sample and places it in the instrument. The sample is lowered gently into the probe on a cushion of nitrogen so that it sits in the centre of the magnetic field and the radio coils. Under the control of the computer, the instrument applies several, typically 16, pulses of radio waves to the sample and collects the responses, called resonances. These resonances are summed up by the computer and processed to give a spectrum. This takes about 5 to 10 minutes. Here is the spectrum of ethanol. The peak to the far right is that from the TMS reference. By definition, this is at 0 parts per million, ppm. The distance leftwards along the horizontal axis is called the chemical shift, and it is measured relative to the peak that is obtained from the hydrogen atoms in TMS. The chemical shift of a peak gives information about the molecular environment of the hydrogen atoms that it represents. The peak at around 1 ppm is caused by the CH3 protons. That at approximately 1.6 is the OH proton, and that at approximately 3.5 ppm is from the CH2 protons. The area under each peak is proportional to the number of each type of proton. This is calculated by the computer and represented by the step height of this integration trace. A closer look at the spectrum shows that the peaks are in fact split into groups of peaks called multiplets with particular patterns. This is called spin-spin splitting. It is due to the influence of the magnetic field of adjacent protons. Two adjacent protons split a peak into 3 with heights in the ratio 1 to 2 to 1. And 3 adjacent protons produce 4 peaks with height ratios 1 to 3 to 3 to 1. This is sometimes called the n+1 rule. Interpreting proton NMR spectra can thus provide a great deal of information about molecular structures. The same instrument can be used for NMR of other magnetic nuclei. A useful one for organic chemists is carbon-13 NMR. All that has to be changed is the frequency of the radio signals.
So for NMR spectra, you're going to have to be able to interpret a spectra and try and match it to a particular molecule. Or if you're given a molecule, you would have to predict the spectra. So there's a couple of things that we can use to explain why this molecule corresponds to this NMR spectrum. One is the signal location or the chemical shift in parts per million, and that's down here in blue. Next would be the number of signals. So you can see there are a total of 3 signals, and they're color coordinated. Then you have signal area or integration, and that's not shown on this particular spectrum, but we'll talk about that. And the signal shape or the splitting pattern. And so you can see for signal 1, there's only one peak, and that's called a singlet. Signal 2, this is one signal, but it's split into 3 peaks. That's called a triplet. Signal 3 is one signal, but split into 4, and that's called a quartet. So we'll talk about what is the rule to determine splitting. So first is chemical shift, and so on this graph you can see at the bottom this is the chemical shift in parts per million, so from 0 up to 12, and you can see where different functional groups, protons on different functional groups would show up. Do you have to memorize this? The answer is no. You can see there's large ranges for certain protons. So for alcohols, right, anywhere from 1 up to 6. You do not have to memorize this. Remember, for infrared spectroscopy, though, you will need to know approximate wave numbers of functional groups. But for this, just get in the habit of knowing that your signals are relative to 0 parts per million. So you won't see anything that is related to the actual molecule at 0 parts per million. You maybe see a signal, but that is due to that standard that you saw in the video, the TMS standard. But also get into the habit of looking at a spectrum and noting the relative locations. So if you're closer to 0 parts per million, we would say protons in this area would be shielded. If you're further in chemical shifts, so going towards the 12 parts per million region, we would say that is deshielded, the deshielded region. So this is what we mean by shielding and deshielding. If you look at the signal for the red protons, you would see those show up at 1 parts per million. But then as you start to add or replace a hydrogen with more and more electronegative atoms, you can see that the signal gets more deshielded, right? The chemical shift is getting higher. So if you replace a hydrogen for, here in this case, an I, a Br, a Cl, or an F, you can see that the signal increases. So you're deshielding those protons. Down here you can see that there's also an additive effect, right? So here we've gone from 1 part per million. If we replace one hydrogen with a chlorine, we increase significantly. And now if we start here and start increasing the hydrogen, or substituting the hydrogens for chlorines, we get even more deshielding, and so our signal goes up. So you could understand then why in this molecule that the protons closest to the electronegative atom would have a signal that is most deshielded, or a higher chemical shift, 3.3 parts per million, than either of these two hydrogens. And then if you're comparing these two, right, these two hydrogens are closer to the electronegative chlorines, so they're going to be not as deshielded but more deshielded than these hydrogens, which are the furthest away. All right, so this table is coming straight out of your book, and it's showing you approximate chemical shifts for different protons, and so you can see different environments, right, where you would expect these to show up. Now again, you don't have to memorize these, but keep in mind the shielding and the deshielding effect, right? So as you have hydrogens that are either directly connected to or close to electronegative atoms, you can see that the chemical shift increases, or we deshield those protons. Okay, so now let's look at the number of signals. So for this molecule, remember this is a ketone, the functional group is a ketone, you have a total of 3 signals. Now the question is, why are there 3 signals? I mean, this is a CH3 group and this is a CH3 group, but why are they different? So first of all, let's look at each of the carbons that have hydrogens. So a general rule written in red for you is that hydrogens that are attached to the same atom in an acyclic molecule, so not in a ring, are equivalent. So we would say these 3 hydrogens attached to this carbon are equivalent. And if they are equivalent, they will have a signal, but those signals will perfectly overlap. So it would look like just one signal for these hydrogens. Now that's the case for these hydrogens too. These 2 hydrogens are attached to the same carbon, or the same carbon, so they would be chemically equivalent. They would have signals, but they would be overlapping, so we would have just one signal for these hydrogens, not 2. Not 3 for these hydrogens, even though we have 3 of them, just one signal. Same thing here. These 3 hydrogens are attached to the same atom, the same carbon, and so we would only see one signal, even though there are 3 hydrogens for that. All right, so now if the hydrogens or the protons are not in the same electronic environment, okay, They are not chemically equivalent. So you can easily see that with this alcohol. Remember, an OH group, that would be an alcohol. So this hydrogen, this proton, is not equivalent to any of these that are attached to the carbons. So remember, in bond line structures, we don't draw in the hydrogens, but we have 3 hydrogens attached to this carbon. We have 1, 2, 3, so 1 hydrogen attached to that carbon, because remember, carbon likes 4 bonds, 2 attached here, and 3 attached here. Okay. Now, if we think about shielding and deshielding, we would say that the hydrogen attached to this carbon would be the most deshielded relative to the hydrogens attached to the other carbons, because it is attached to a carbon that's attached to an oxygen, a very electronegative atom. So that's going to make this hydrogen unique and different from all of the other hydrogens. So that means we would have another signal apart from this one for the alcohol proton. We would have another signal for this hydrogen. Now, we can think about the hydrogens here, here, and here and think to ourselves, are they chemically equivalent? So again, if you think about electronegativity, even though this is a CH3 group and this is a CH3 group, these hydrogens are closer to that electronegative atom. So they would not be identical to these hydrogens. So these would be totally separate signals. Now, if we think about these hydrogens, are they chemically equivalent to any of the other hydrogens in the molecule? The answer is no, because if we look at the connectivity, right, this carbon is attached to 2 other carbons, and you don't see that, and that's it, and you don't see that in anywhere else in the molecule. Now, yes, this carbon is attached to 2 other carbons, but it's also attached to the OH, and you don't see that for this carbon. So if it's not in the same environment, then it would not be equivalent. And so if it's not equivalent, each of those hydrogens would have its own signal. So I would see a signal for this hydrogen of the hydroxyl group. I would see a signal here for these 3 hydrogens. I would see a signal here for the hydrogen that's attached to that carbon. I would see a signal for the 2 hydrogens attached to that carbon and the 3 hydrogens attached to this carbon. So that would be 1, 2, 3, 4, 5. So I would predict 5 signals for this molecule, because I said first that the hydrogens attached to this carbon are chemically equivalent based on this rule, but they are not equivalent to any of the other hydrogens in the molecule, so they would give their own signal. All right, so now you can start to predict about where they would show up, right? And so we kind of talked about that already, shielding and deshielding. So you would expect the hydrogen, the hydrogen attached here would probably be the most deshielded because it's closest to that electronegative atom. And then it would kind of be a toss-up between these two, right? But what you would know is that this signal would be somewhere, anywhere here, but these signals would be to the right of it. All right. Now, another way to figure out whether or not you have equivalent hydrogens is to look for symmetry in a molecule. So if you look at this molecule, right, hopefully you can clearly see that if you were to cut this molecule in half down that oxygen atom, the left-hand side would look identical to the right-hand side. So that's what we mean by symmetry. The 2 halves look identical. Now, that means then that hydrogens are equivalent on both sides. So the black hydrogens on the left-hand side are equivalent to the black hydrogens on the right-hand side. Same thing for the blues, same thing for the reds. If they're chemically equivalent, remember you only see one signal. So that's why in this NMR spectrum you see 1, 2, 3 signals, because you have here for the red hydrogens, you have 6 hydrogens that are chemically equivalent. Now, if you don't see the symmetry, okay, another way is to look at the connection, right? This carbon is connected to a CH2. You see that exact same connectivity over here, right? This carbon's connected to a CH2. Same connectivity for the blue hydrogens, same for the black hydrogens. And another way to look at it is if you look at the black hydrogens, right, they would be the most deshielded. So remember, deshielded is down here. And they would be the most deshielded because they're closest to the electronegative atom. And then you see that the blue hydrogens, which are further away, would then be a little more shielded, but more deshielded than the red hydrogens, which are the furthest away from the oxygen. So if you look at these 3 examples down here and you're trying to figure out the number of signals, right, look for symmetry, okay? Either look for symmetry or look at the connection. So I could draw a plane of symmetry right down the middle and see that these 3 hydrogens are equivalent to these 3 hydrogens, right? So if they're equivalent, this would be one signal, so we'll call that signal A. This hydrogen has nothing, is not symmetric to anything else in the molecule, so this would be a separate signal, so signal B. And this hydrogen, this is the only one that you see connected to an oxygen. You don't see an oxygen anywhere else in the molecule, so this would be signal C. So this molecule would have a total of 3 signals, okay? And you could predict this would be deshielded, more deshielded than the B signal would be more deshielded than the A signals, okay? All right, what about this molecule? So here we have a ketone. That was an alcohol. This is a ketone. Again, you could draw a plane of symmetry down that middle carbon, and each half would look identical. So you would have one signal for all 6 of these carbons. So one signal for this molecule. Okay? This carbon doesn't have any hydrogens. We're only focused on hydrogen right now. So one signal. If we look at this molecule, if we look at benzene, okay, remember that benzene, even though we're drawing double bonds here, here, and here, this molecule has resonance. And so really you could draw, each carbon-carbon bond in this molecule has a partial double bond to it. And so that means each carbon is basically the same. And so the hydrogens then are connected to the same carbon in the same way. So that means benzene would show also only one signal. Okay? Right? And so that's showing you here, this is benzene now at the top, where every carbon is connected to a hydrogen. So you can see those planes of symmetry. You could also think about the resonance structure that we draw of benzene, where it's every carbon is sp2 hybridized, so it all has partial double bond character. So that's what's going to make these the same. Okay. Now, if we look at the molecule at the bottom, the difference here is that we have substituted this hydrogen for fluorine, this hydrogen for chlorine. And when we do that, we lose the symmetry, right? We don't have symmetry anymore. And so for this molecule, benzene, we see one signal, but for this one at the bottom, we're going to see 4 signals for our proton. Okay? This would be a different signal because it's attached to a carbon that is attached to a carbon with a fluorine. This would be a totally different signal because it's attached to a carbon that is attached to a chlorine. Okay? So this would be your most deshielded hydrogen, followed by this one in green. Now these two are not the same because if you look at the connectivity, this red hydrogen is attached to a carbon, which is closer to the fluorine than this purple hydrogen. So you might have to go out, right, looking at connectivity, not just the atom immediately connected to it, to the atom that has the hydrogen attached. You might have to go one out. And that's how you can see that these are different. So the red hydrogen might be slightly more deshielded than the purple hydrogen because it's closer to fluorine than the purple hydrogen, which is further away from fluorine but closer to chlorine. But this being the more electronegative atom makes these the most deshielded, followed by the green, followed by the purple. All right, so this is just sort of summarizing. If you can't see shielding, deshielding, if you can't see symmetry, then just talk it out in your mind or out loud, the connectivity of the hydrogens. Okay, so this alcohol is trying to explain to you why you would see a total of 3 signals. Okay, so this molecule, you would have 3 signals. Now, right away, you can see that this H, which is attached to an O, would be a signal because you don't see an oxygen in the rest of the molecule. But if you look at the blue hydrogens, so remember our rule, if the hydrogens are attached to the same atom, they're equivalent. But these are different. They're not in the same connection as the hydrogens attached to this carbon, right? This carbon's at the end. It's only attached to one other carbon. That is a different connectivity than this carbon, which is connected to a carbon and an OH. Because of that different connectivity, that means that these blue hydrogens will have a separate signal than the red hydrogens, and then the green hydrogens by itself. Okay? So here's another example. If we look at connectivity, so this molecule is going to have 2 signals. Okay? These blue hydrogens are connected to a carbon that is connected to a fluorine. So you would think right away these are going to be the most deshielded because they're closest to the electronegative atom. Now these hydrogens boxed in green are all equivalent to each other because if you look at the connectivity of these hydrogens, it is no different if you describe it than these or these, right? These hydrogens are connected to a carbon, which is connected to this carbon, which is connected to a carbon, another carbon, which is connected to the fluorine. Exact same thing for these, exact same thing for these. Okay, so you would only see a total of 2 signals. So getting back to this molecule, we already went over that you would see a signal, a separate signal for all of the hydrogens connected here. So remember, bond line structures, we're not drawing in hydrogens, but you've got 3 hydrogens at this carbon. So remember to draw in your hydrogens if you can't visually see that. You've got 2 hydrogens at carbon C and 3 at carbon D. So remember, carbon likes 4 bonds. That's why I put a hydrogen here. It's got 1, 2, 3. So that 4th bond must be to a hydrogen. Okay, so now let's look at signal shape or the splitting pattern. And so in that video, it said that the splitting has to do with adjacent or neighboring hydrogens. Okay, so if you look at this molecule, right, signal 1, so we know why there are 3 signals, right? We know that these hydrogens are in a different chemical, electronic environment, are connected differently than any of the other hydrogens, so that's a signal. Same thing for these, same thing for these. But the question is, why are they split? And the video talked about an n+1 rule. And so that letter N stands for the number of hydrogens you have on your neighbors. So for this blue signal, if we look at the number of hydrogens we have on our neighbors, so a neighbor would be any atom that is directly connected to the atom that's bonded to our hydrogens. So this only has 1 neighbor, and there are no hydrogens on that. So the n+1 rule, says here that if n is 0, then this would be 1. And you can see this is a singlet. It's only 1 signal. All right, let's look at the green signal. Here, the n+1, we look at this carbon. There are no hydrogens. That's 1 neighbor. Let's look at this carbon. There are 3 hydrogens. So 3 plus 1 equals 4. And if you look at this signal, you see 1, 2, 3, 4. So that's where we get the 4. If we look at the red signal, look at our neighbors here. We have 2 hydrogens, so 2 plus 1 equals 3. And if you see that, you have 1, 2, 3. So this is one signal, but it's split into 3, so that's called a triplet. This is one signal that is not split, that's called a singlet. And this signal is split into 4, that's called a quartet. Okay, so this is what we mean by splitting. So if we look at the signal for HA, the red hydrogen, we look at the neighbors. Here we have only one hydrogen, so remember we're doing that n plus 1 rule. So here for the HA, the red hydrogen, n plus 1 rule, we have one neighbor, so that equals 2. And so we have a doublet. Again, if we look at HA, we have 2 neighbors. So 2 plus 1 equals 3. We have a triplet. Let's look at this one. We have 3 neighbors, so 3 plus 1 equals 4. We have a quartet. Okay, so this is telling you the number of neighbors and then the multiplicity. Okay, so you can see we're stopping at 6. Anything higher than 6, you could just call it a multiplet, right? If you can count those, you could say, I'm sorry, this is actually, yeah, if anything higher than 7, actually, this is septet. This is the number of neighbors because it's n plus 1. You could just call it a multiplet, okay? If you see at the bottom in red, it says that alcohol and aldehyde protons are not split. So anytime you have an alcohol, okay, so remember an alcohol looks like this. This is always going to be a singlet, okay? An aldehyde looks like this. These will always be singlets, okay? All right, now what is very important for you to remember, after you've determined the number of signals that you will see in a molecule, right? Either you do it by connectivity, or if you see symmetry, or think about shielding, deshielding. Once you've determined that this molecule you would have you would have one signal, right? Because these hydrogens are equivalent. If you wanted to do the splitting according to the n plus 1 rule, you have to remember that equivalent protons cannot split one another. So it's like you don't have any neighbors here because these are equivalent. So because if we're looking at these hydrogens, right, they're all the same signal, they cannot split each other. So it would be 0 and all you would see is a singlet. Okay? So remember that equivalent protons cannot split each other. Now also remember that a neighbor means it has to be directly bonded to the atom that the hydrogens in question is we're talking about. So HA, right, to be split, it would have to have a hydrogen on this. This is my neighbor. This is not my neighbor. It's too far away. So n plus 1 is your neighbor, not anything else. Okay? Okay, so if we look at this molecule, we went through how many signals we would have. So let's go through that again. We said this would be one signal. We said we have 3 hydrogens, so that would be another signal. Remember we said we have a hydrogen here, so that would be another signal. We've got 2 hydrogens here, 3 hydrogens here. Okay, so we have a total of 3 signals. So we have A, B, C, D, and E. Okay, let's look at the splitting for each signal. Okay, let's start with A. So remember our n plus 1 rule, right? My neighbor for the hydrogens on A, this is my neighbor. I have 1 hydrogen, so according to the n plus 1 rule, I have 1 hydrogen on my neighbor, so that is 2. So that would be a doublet. Okay, let's look at B. I have to look at all of my neighbors, right? So for A, I have 3 hydrogens. And C is also my neighbor. I have 2 hydrogens. So I have to add up all of my neighbors. So I have 3 plus 2, and then don't forget to add the 1. So that's 6. So that's going to be a sextet. Let's look at C. Remember, I have to add up all my neighbors. So I have 3 hydrogens here. I have 1 hydrogen on my other neighbor, and then I have to add 1 according to the n plus 1 rule. So that's 3 plus 2 is 5. So that's called a quintet. Let's look at D. I only have 1 neighbor for D, so n plus 1 is 2 plus 1. So that's a triplet. And for E, we said alcohols and aldehydes are never split, so that's going to be a singlet. Okay, so that's how, if you're given a molecule, first thing to do is go through and figure out how many signals do you have, and then figure out your splitting. Okay, and so that's what the NMR spectrum for this molecule would look like. So everything's color coded for you, right? We went through that already and figured out the splitting. Okay. All right, so now let's look at the signal area or the integration. So integration refers to how many hydrogens are responsible for a signal. And so for this molecule, it's pretty easy to tell. Now you will see on your exams or your problem sets a number like this written above the signal. That number is the integration, or it's telling you that for this signal, there are 3 hydrogens responsible for that signal. Whoops, I'm sorry, that should be a 2. There are 2 hydrogens. Let me fix that. This should be a 2. This should be a 3. And this should be a 3. Okay. So again, this number is telling you how many hydrogens are responsible for that signal. So it's color coded for you. So the green, you see it's a CH2. That's where I get the 2 from. Okay. The red, CH3. That's where I get the 3 from. The blue, 3 hydrogens. That's where I get the 3 from. I apologize for mislabeling that. So if we look at this alcohol, the one we just did the splitting for, hopefully this is all correct, right? You can see that for this signal, the red signal, you have 3 hydrogens, and so that corresponds to 3 hydrogens giving that signal. 2 for the purple, 1 here. Here you have 6, but it's only 1. I'm sorry, a sextet, but it's only 1 hydrogen, and here you have 3, right? So this number is the number of hydrogens. So even though this signal is a sextet, right, that's the splitting, it's only 1 hydrogen, right? Even though this is a doublet, it's 3 hydrogens. So these numbers don't correspond to the splitting, it corresponds to the number of hydrogens. All right, so some of the integrations or the number of hydrogens you'll start to recognize patterns, and these are the 2 most common patterns that you'll see with NMR. If you see a singlet with 9 hydrogens, this is the kind of group you should think, and this is called a tert-butyl group. So 9 hydrogens, think 3 CH3 groups, right? 3 plus 3 is 6, plus 3 is 9. And because it's a singlet, that means that the neighbor has no hydrogens on it. So remember, carbon likes 4 bonds. So this is the only way right now that you know of that you could get a singlet of 9 hydrogens. Here's another one. If you see 6 hydrogens and it's a doublet, remember the n+1 rule, think of something like this, right? Because that would mean that the neighbor would have to have a single hydrogen on it. And 6 hydrogens, the easiest thing to think of is 2 CH3 groups. Okay? So this is called an isopropyl group. And you should also see in that NMR spectra this signal, which is 1 hydrogen, that's the integration, but it's split, right, by 6 hydrogens. So 6 plus 1 is 7. So 1, 2, 3, 4, 5, 6, 7. Okay? So if you see this in an NMR spectrum, 1 hydrogen split into 7, 6 hydrogens in a doublet, think of this group. Okay, so if we look at these 3 different molecules, and they are different if you look at the connectivities, right? You probably couldn't tell them apart by infrared spectroscopy or even mass spec, because they're all gonna, if you determine the molecular formulas of the 3, they are identical. If you looked at the 3 by infrared spectroscopy, you're going to see an sp2 carbon to hydrogen stretch. You're going to see an sp3 carbon to hydrogen stretch. You'll see an sp2 to sp3 carbon stretch. But you have that in all of the molecules. So what you want to be able to do is distinguish these, and you're going to have to put together NMR or NMR with IR, or maybe NMR with IR with mass spectrometry in order to distinguish these 3 molecules. So by NMR, you could easily distinguish these 3, right? If I gave you 3 unlabeled vials and I said in each of the vials you have one of these molecules, run the NMR spectrum and figure out which is which, you could easily do that based on the number of signals, right? So this molecule would have a total of 3 signals. So look at the connectivity, right? Or look at symmetry, and you can figure that out. This molecule would have 4 signals, right? This hydrogen is totally different from this hydrogen because if you look at the connectivity, this hydrogen is connected to a carbon that's connected to carbons that are connected to CH3 groups, and you don't see that connectivity for the orange hydrogen. This molecule would only have 2 signals, and if you look, right, there's a symmetry. You could do it this way or you could do it this way. Either way, the red hydrogens are equivalent and the blue hydrogens are equivalent. So you're going to have to be able to put together all of the techniques that we've talked about so far to identify molecules. Okay, so for carbon NMR, it's a lot easier, I think, than proton NMR because all you have to worry about is determining whether carbons are chemically equivalent, exactly how you did for determining if protons are chemically equivalent. You do not have to worry about splitting. For carbon NMR, all of your signals will be singlets. So if you look at these 3 molecules, you could easily tell them apart by their carbon NMR. Okay, so it's telling you that this one would have 4 signals, and if you split this molecule in half, each side looks identical, right? So you could draw a plane of symmetry right down the middle. So you would have 1, 2, 3, 4 different carbons, so in different chemical environments. So for this, we're talking about carbons, not hydrogens. Okay, so don't forget about these carbons in the ring. A lot of people forget about those. This molecule, right, you could then split it this way, right? And now you have 5 signals. So this carbon, 2, 3, 4, and 5. So just as the hydrogens connected to this carbon were not equivalent to this hydrogen, neither are the carbons. And here you have 3 signals, right? So you've got a couple planes of symmetry here. You have this carbon, so that's 1, 2, and 3. Okay, so really one of the major keys is being able to recognize chemical equivalency. So if we looked at this molecule and I asked you to predict how many carbon signals you would see in the NMR, so not proton, but carbon signals, look for your planes of symmetry, right? So think about how you could cut this molecule up and would each side look identical. And the answer is you could do a plane of symmetry here or here, and then figure out your equivalent carbons. So don't forget about the carbons that are in the ring, even though they're attached to something, right? So you're going to have to do this on your final. Predict the number of carbon NMR signals. So here's that molecule, right? Here are your carbons, and I color coded them based on the number of signals. So you would only see 2 signals for this molecule. So don't forget about the one in the ring connected to something. So this carbon is in an identical environment to this carbon, so that's 1 signal. And all of these carbons are identical. They're in the same chemical environment, so they're identical. So you would see 2 signals. Now notice for carbon NMR, the chemical shifts are much, much higher than proton NMR. So we went up to about 12 for proton NMR. Here we're in the 100s. And so you can see approximately where carbons show up in different functional groups. So it's kind of the same shielding deshielding effect, right? So you would expect that the green carbons would be this signal. It would be more deshielded because they're directly connected to an electronegative atom. And then this signal would be due to the orange carbons that are part of the double bond. Okay? And then these are all going to be singlets. Remember, for carbon NMR, we don't see any splitting observed. All right, so I put a lot more videos from Khan Academy on Canvas for you to practice determining equivalency and splitting. So make sure you take a look at those if you're having trouble. There's also, you've got tons of problems in the book to help you as well.